For lesson 4. Okay, so I just want you to take note that after logarithm decrement, okay, once a force vibration start, okay, this so many videos, we have a lot of mistakes. Okay, not a lot, but rather than when we are dealing with the talking about the analogy of this forcing function. When we are talking about this thing, we most not most but part of the things aren't correct. They mix with some correct stuff but also mixing with a lot of incorrect stuff. So I just want to make clear first. And then we talk about the first part actually in lesson 4 we talk about logarithm decrement. We say that estimating the damping factor for the experimental results. Because the purpose is actually to estimate the damping factor for experimental results by using this formula if you remember. Okay, so the x and the xp and xn plus p, the point is just, let's say you pick this point 1, n is 2 points from, n is how many points from your original point. Let's say you want to pick 3, so there is 1 point and 2 point from point 1, right? So that's why n is 2, 2 plus 1 is equals to 3, and so on and so forth. And then with this thing, then you can actually set up equation to actually solve for your damping factor. So it's just to show you the relationship between two amplitudes. Okay, two amplitudes. So nonetheless, yeah. And then we talk about forcing function. We describe how things are actually yeah. So not want to talk about it much. So before going to forcing function, I just go back to logarithm decrement first. So to set out the equation, you have to really determine the x1 and x2, and you have to know since there's oscillation and eventually it will decay to 0, you know that this is the underdamped. So our x is actually using the underdamped formula, and then the reason why we choose the e exponential is because sine itself is sinusoidal. Okay, and then when you're taking points from this point and this point is actually in terms of exponential, so you just take exponential points and that's all. If you don't understand, you can just go back to my videos. That part is totally explained very clear. And then you also derive the general formula for the for what just now we have explained earlier. Okay, general formula for this case, we have derived this, so you can just head back to to watch the video on it. And then for forcing function, um, we use the same method that we use. We have to understand the system first. Because we didn't understand the system, okay, this is why at my last stage I actually cock up. I didn't realize that it's more complicated than this system itself. We only know that okay, the amount of forces acting on the body is these things. Okay, is these things. However, when you go into the natural frequency things, gets a little more messier. But nonetheless, you understand the movement, that's all, movement, and then FBD, you just know that is the amount of forces acting on the mass. The first part is easy, you just set a summation, and then you do out a equation based on the FBD, and then you do whatever thing, you rearrange, divide everything by mass. Okay, this is a typical step for all what we have done earlier. And then eventually you can acquire this equation, and this is a second order non-homogeneous equation. And then we talk about how do we actually use the second order general equation, homogeneous equation, to actually solve for x in this case. We explain why we do want complementary function because it's a steady state. Steady state we only use the particular integral and that's it. And then this is why we talk about particular integral for the rest of the whole thing. And then we took a trial function, and then we describe why x is being replaced to sf. And nonetheless, the analogy may be wrong, the definition may be wrong. And then we talk about the phi angle, which is also cock out, but nonetheless the meaning is about there. And then we use this equation, we differentiate 2 times, and then we set back into this equation. You rearrange again, set up, and then you apply trigonometry, okay, and then you rearrange again, and then we use a lot of substitution. Okay, we use the damping factor substitution, the natural frequency substitution, and nonetheless in the later parts we use the beta substitution. Remember the beta, the frequency rate. Okay, so these are the 3 stuff that has been that are in your data sheet. Okay, in your data sheet. So in your data sheet, this all of those things you should have a clear idea of what they are, and then also the beta, and then after which you derive you derive an equation that can describe a vector polygon, because nonetheless what you are doing over here is eventually let your equation to be equals to 0. When the equation equals to 0, you can actually set up a polygon. Okay, what is the polygon itself? So we will just go to the polygon. So as you can see, in order to make the polygon, you have to make sure everything is in terms of cosine, so that there's no difference in sine and cosine, because all you are dealing with is one dimension. Cosine is just dealing with a cosine theta, which is in this dimension, x dimension, I would say. Now while you're putting into a vector form, there are many different x dimension in a sense, and then it's like a summation of x. Okay, so if you remember where are we? The analogy for the ax plus bx plus cx plus dx equals to x, and then this x should be 0. So this is all of the cosines. So if it's sine, then you have a different graph, you have a different polygon, not polygon but a different shape already. If it's sine graph, if this is cosine and this is sine and then this is sine and then you put a cosine back again, you are like here and there everywhere. So it's not very cool. So make sure everything are cosine, and then you do a plot to determine the directions. And typically, the plot itself will look like this, where the kx is larger than the acceleration magnitude. I don't know why. And then we set out an equation to using this relationship. Okay, we use Pythagoras theorem to solve for the magnitude for force for this thing over here. We try to solve the magnitude for this, and therefore you use the Pythagoras theorem, and you do a lot of rearrangement and stuff. You get this equation, and this equation nonetheless may be provided. I think it's provided. So it's over here in the test. So if you have your forcing function, you know your spring constant, you know all the natural frequency and stuff, you can just sub it in. So typically you need to go and practice. Okay, you need to go and practice how to use them all. And then after which, since we also know that we have a theta angle, if you remember, there is an angle over here, right? There is an angle over here that relates to all this, all these things, the spring constant, the acceleration, and whatsoever, and damping factor itself. So this forcing function itself relates all these 3 terms together. So therefore, in order to fully relate, you have a angle, because you have a phase shift, which is being explained not very logically. So the forcing function is this one, while the displacement vector, okay, is moving a phase behind a forcing function, okay, because of other unknown forces that may be lost during the process. So there's many complications which I have no idea how to solve, but nonetheless we we derive the understanding for we derive a equation for phi, okay, using the tau tangent. Okay, we since we know all these things, you can just straight away use Pythagoras theorem and solve for your thing while rearranging. Make sure when you see k, when you see this, case, make sure, if you want to rearrange, make sure everything divided by k, or maybe, so you have to really put in an effort to really know how to simplify the equation, so that typically you want to simplify the equation in terms of beta, okay, beta for forcing function, okay, beta or whatever thing that is, bracket square type of thing. So you can see at the end of the day you have like a bracket square. We don't want anything like 2 and then delta square, beta square, and then plus 1 minus beta square type of thing. So we don't want it to be in this form. We want everything to be bracket. Okay, so in order to be neat. So this really requires a lot of skills. And then we also talk about lastly the damping system, what is considered unacceptable. So this one is resonance. We don't consider it anymore. We don't consider it to be acceptable unless you put a damper to damp out the resonance itself, so that you will not spoil the system or damage the system. Nonetheless, I have cleared the general concept of what is chapter 4. If you, yeah, but if you, I would suggest you go and watch this video. Okay, you may understand what is actually resonance, and then also this video, these experiments that would really help you to understand the resonance, and may actually help you to invent a not invent but rather understand how to set up a force vibration system. Okay, we don't want, from still after learning so many things, we don't even know what is the damper itself, and then how does the damper being applied, how do we apply things, and then what is actually the resonance, how to describe the resonance in this case. Okay, in fact we know how to describe resonance, but rather than we don't know how we achieve the resonance, I would say. And then these are the things, yeah, it's pretty tough. So I'll leave you to think for the future. So in the future, if you know what it is, then you just do a video and touch up on this. So I'll just see you there, and lesson 5 to be done soon. Bye bye.